that was actually launched by Bernhard last year on this very stage, where he said that we should have a feasibility study that involves the community in defining how we use it, how we build it, and what the requirements should be. And we have taken that to heart, and looking at what we need to do to deliver the sort of lunar pilot plant that's been discussed by the minister and by various other people to produce oxygen and metal on the moon. We introduced the sort of roadmap to these pilot plants last year to the member states. And if we could have the slides on, please. Yes, thank you. Oh, you do it. So as you can see here, this is what we presented to the member states. And you can see here that we have not just one stream of work, we have parallel streams of work. Why? Because if we were to do this sequentially, we will never be in time to deliver what we need to deliver in a usable time frame. So the words that is being used for these conferences are to accelerate. And how do you accelerate? You try and run as many things as you can in parallel to get where you want to be. In this case, for us, is to have a lunar pilot plant that will be potentially a mission on the EL3, which, as we heard from Giorgio, is going to have a capacity between 1.5 and 1.8 tons payload. And as mentioned as well, there's been a study, and we were aiming to produce between 1/10 and 100th of what the ESRIC-G target for oxygen production was, which is 50 tons of propellant, which in oxygen terms equates more or less to 45 tons. And we worked on that alongside the other developments that we have. We have a pointer? No pointer. So, okay. I'll just move my hands like a good Italian. We started in 2019. We started this work on several streams. We have the process de-risking activity, of which we have the company that will be also on stage, Metalysis, working on taking inherently a terrestrial process that is geared to produce metal and turn it upside down and say, okay, metal is important, but oxygen is way more important. And at the same time, there was work started to be done in the area of, let's make a demonstrator out of this process. And this is all in line with what also Jerry said before, that you have stages in which you do the terrestrial, you have a demonstrator, then a pilot plant, and then eventually a full capacity plant. And still we are in the phase 1. We are going to launch the terrestrial pilot plant feasibility study, G2.1. We already are working on the S1.1, and there will be David Beans talking about that, and the CDF study as well. And of course, some critical technical developments to be carried out. But here we are trying to show not just that you have these 3 streams of work, but how they interconnect. Because sending a plant in space, I'm a chemical engineer, so space questions, not for me. But what I know is what it takes to run a plant, and how many times you have to stop and restart, how many times you have to do maintenance, how many times you have to run with problems. And if you were to learn that on the moon, it's going to be a big problem. That's why we need an analog, a terrestrial pilot plant that we can learn how to break it, how to use it. But most importantly, as we have been discussing, this is not a no one nation, one agency effort. We can't do that on our own. So that's why, embedded in the concept of doing the feasibility study, we wanted a strong community interaction to tell us a lot of things. I'm not going to carpet bomb Brigitte's presentation, but things like user needs. Who's going to use it? And how do we make it an open architecture where people can come, have a baseline, and say, my technology is better than yours. Yes, prove it. So you don't have to build the infrastructure, it's already there. So we help you by taking away certain costs, which are unavoidable, and contingently de-risking the technology, as we have heard from the other talks, Jerry included, in which if we want to do this commercially, who's going to do it? Who's going to take the risk? And for what markets? We have to work on all of these aspects, and this is one fundamental piece, of course. Not the only piece, but one of the fundamental pieces. Having said that, I'm not trying to carpet bomb Brigitte's presentation. Off you go.
Thank you, Mel. So, good afternoon. Many key messages have been dispatched already this morning and by Mel. So, but my intention was first to come back on about the necessity of a ground-based pilot plant. So, as Mel just said, the challenge is so high that you need to be really agile in your approach, and you cannot run things sequentially. But on the opposite, you have to progress on the development phases in parallel, because basically all those phases are informing each other in an iterative approach, and this is what we try to do. An important remark is to say that doing all this work in parallel and over time require the availability on the long term of well-designed facilities. So this is basically what we try to do at ESA and in collaboration with key partners like ESRIC. We start from process optimization by internal research, by investigating scientific aspects and contracting low TRL technology development. We are contributing to develop lab research capabilities like the ISRU lab platform in ESRIC. And we try to anticipate on gaps and critical items by initiating some studies regarding the space system demonstration and operation, defining a potential mission, performing some concurrent design facility studies, preparing for ISRU payload demonstration in space, and last but not least, planning for a ground-based pilot plant supposed to become an analog serving a wide community. So, as I said, those phases of development needs to run in parallel. We need to tackle challenges associated to adaptation to space, but as well to industrialization of the process. And here, a ground-based pilot plant is playing a key role. First point to highlight is about the scalability challenges. Scaling up is rarely a linear increase of capacity, so we are discovering additional challenges where we start to study this scaling of the process and of the technology. I think it was mentioned this morning, the importance of gaining in operational knowledge. It is really critical to learn how to do things, what is the level of automation we should have, how do we control the processes, what about the maintenance, the troubleshooting, the crew time needed, the spare parts needed to embark in the future. So this operational know-how and knowledge is really something that a ground-based pilot plant can help defining. A third point to highlight is all the activities that regarding de-risking at system level that can be performed in a ground-based pilot plant. And it is allowing you to tackle issues like, for example, safety, which is as well very key for our astronauts and our facilities. The intention in this platform is really to go to an end-to-end process, so contributing to a system view, performing long-term demonstration campaigns, and by doing this, we hope to be able to define in a robust way parameters like efficiency, which are as well really key to anticipate on the sustainability of a lunar pilot plant and on lunar activities, and reliability, which are key aspects for space demonstration and space system operation. A few words about the concept of this ground-based pilot plant. Two drivers that I wish to highlight this afternoon. The first one is about the selection of the core extraction process. So at ESA, several studies were performed to identify or to study different candidate technologies and processes. And the first trade-off, first selection has been based on, what do I need first to be sure or to de-risk the economically sustainability of my system. And so the trade-off was driven by extraction yield. And as a result, molten salt electrolysis was the winner because it has been really demonstrated that we are able to extract essentially all the oxygen which is available in the lunar regolith. The studies led us so far to the current configuration of using calcium chloride as molten salt and operating around 950 degrees. But there will be more presentation during those 3 days about that. The second key driver, mentioned already by Mel and by Bernhard as well this morning, is that we wish to have a concept of open architecture for that platform. It is challenging, we know that. So we have defined some boundaries for this platform. Where do we start and where should we end? So basically, we wish to start from regolith preparation for an optimized performance of the core process and going up to storage of products, oxygen and metal, which are fit for downstream application and potentially post-processing. Aside of the core extraction process, which is like really a cornerstone in this development, we wish to open that platform, to have this platform to really become a test bed for you to come and do your science, test your technology, as we are all convinced, as Mel mentioned as well, that it has to be a joint effort considering the risk, the cost of this ambitious challenge. Okay, I think you understood it already from the presentation this morning. The ground-based pilot plant is going to be hosted by ESRIC. It will be surrounded by complementing facilities like the dusty thermal vacuum chamber, the lab research platform, ISRU lab will be close by as well. The teams at LIST and ESRIC are already thinking about a preliminary concept for that facility. So first point to highlight is it will be located on the Belleville site. And some preliminary schematics have been created to try, starting from a very important point, which is the daily operation of such a platform. What do the operator needs in terms of supporting infrastructure? How should we organize it to have a smooth operation and to ease the work there? So they are listing some necessary supporting facilities, workshops, etc. And they look at a key aspect, in my view, which are the material and personal flows, because we want this facility to be attractive so that you like to come and work there. On ESA side, Mel mentioned it, we have launched the feasibility study for this platform. The invitation to tender has been launched, but unfortunately the evaluation process is not completed yet, so I cannot say much about the potential outcome. Nevertheless, I can share with you the key task that we have proposed in our statement of work. So the ambition is really to start from a wide community consultation in Europe and beyond. It is our intention to collect your expectation regarding that platform, to eventually become a stakeholder, a user of it. It is our ambition from your expectation to define what kind of topics should be listed in our research and development agenda. it is important to design what kind of testing campaign should be done on that platform. Key aspect as well, what I have called a utilization plan, is how this platform should be operated. We want to engage you into this challenging development. And as soon as we will have collected as well all your expectations in terms of collaboration agreements, what would be the condition for you to join us on board, we will move on to a preliminary end-to-end design for this facility, potentially supported by some critical item study through breadboarding. And as an option, it's not defined yet, we may go further into the detailed design of the reduction module itself. After completing those two steps, we will try to define a master development plan. The idea is to identify a critical path, to identify risk, to discuss about CapEx, OpEx, cost estimation for the development of the platform. Okay, I think that, as I said, the first ambition of this feasibility study is to get in touch with you, to collect your expectations. So we have planned a mini questionnaire for you. If you would like to answer to it, it will be really appreciated. By answering those questions, we will collect you will have the opportunity to express your interest and your wish to be contacted at the next step, when we are going to go into more detail, more practical detail, more specificities of this platform. You have as well an email address to contact us for any question you may have. And in the meantime, you are hopefully answering those questions. I will invite the participant to the roundtable to join on stage. Thank you for your attention.
So just also, we will be at the ESA booth outside, so if you have any questions, you can reach out in person directly to me or to Brigitte if you want to start talking and discuss any details that you have in mind. Please do so.
Thank you both so much. Thank you, Melchiorre, and thank you also, Brigitte. Has just been mentioned to you, Bernhard Hufenbach will actually lead this roundtable discussion. So please welcome Bernhard back to the stage, of course, and also his guests, Karl Hibbits, Kathryn Hadler, Daniel Inocente, Mellor, and Pascal Barbier. There will be an opportunity to constantly ask questions online, and hopefully through the course of the day, if not on stage, they will be answered to you directly so that other people can see the answers as well. Thank you.
Okay, so let's get started. I have a long CV of each of you here in my laptop. I don't want to read it. It's very long and we use too much time. So my first question will be a personal question. And if you can answer it shortly in 1 minute so we don't spend too much time. And I start with you, Kathryn. Maybe you can just tell us who you are. I think most of you know you. But the more interesting question is, what did motivate you to apply for the position as director of ESRIC?
Well, I wasn't expecting that question, so I think full marks for the surprise element. My name is Kathryn Hadler. I'm the director of ESRIC. What motivated me to apply for this position was the challenge. And I bring with me a background in terrestrial mining, terrestrial mineral processing, and then the last few years in space resources. And I think that perspective is very complementary to many of the more space side perspectives that we have in the sector.
Thank you. Very good. Very nice for sharing that. So the first question to you is, we heard all about these exciting ground-based pilot plant. How important is it for ESRIC and the future vision of ESRIC?
For ESRIC, we are really we see our activities. So we do research, we're interested in supporting commercial activity, and we're interested also in supporting, bringing together the community. So the ground-based pilot plant is really the embodiment of all of those activities. For anything meaningfully to be done in space resources, in any space resources process, we need to have complete systems. We need to understand flows between units. We need to understand interfaces. Mel already mentioned reliability, maintenance, all of these topics. And we can't do that on a unit-by-unit basis. We have to do this in an integrated way. And the pilot plant offers us the opportunity to build those systems, to switch in, switch out equipment. And so for us, it's absolutely critical.
Very good, thank you. Carl, so you're next. So same thing. First question: Who are you? and what? As you're a scientist by education and background, I think. What do you find fascinating about the topic of space resources?
Great, thanks. Right. So, Carl Hibbits. I'm a planetary scientist at the Applied Physics Laboratory, specializing in infrared spectroscopy and in the volatile regolith interactions related to the moon. So. Really, that science question is what got me interested in ISRU in particular, to begin with, the actual existence of volatiles in a vacuum environment where they may or may not be thermally stable and there's athermal loss processes. But for ISRU, I think your question is why am I interested in ISRU in particular? I still remember, maybe we're speaking with Ben Bussey, but there are 6 different focus areas in the ESRIC, and ISRU, power, dust, mitigation, extreme access, extreme environments, and I always forget one. Anyway, excavation, construction. But ISRU is really the one that we need to develop, and it can develop, and always involves all the other ones for a true sustained presence. So that's really what got me very interested in ISRU. It is that and excavation and construction in the NASA part, these are probably the 2, and power are kind of the 3 most important ones. And they all work together with all 6. So in reality, I just want to say, let's not just think of ISRU. It's a one big system, as Kathryn was talking about.
So you heard all about the pilot plan. I think you proposed similar things in the United States. Do you think there's a risk we build it, nobody uses it? Or do you think the community waits for it and will ask for making use of it in an intense manner once it's available?
I think that NASA ESA will have to have something like this in order to use it, because verification, validation of your system is essential to both ESA and NASA instrument and mission developments. And in this case, as Mel said, when you go to the moon, that's not the time to learn. We're going to be learning unexpected things. We need to learn the expected problems and the known unknowns here on the Earth. And it's a big system. It's a system of systems. Even the ISRU pilot plant is a system with power and everything else. You have to add VSAT or some power source to it. You have to deploy this from whatever you're landing on. You have to do, as someone said, maintenance and operations. And by the way, it has to last for many, many days, if not years. This is all very different, and this, I think, needs to be demonstrated on the Earth in order to have success on the moon to the most, greatest extent possible. What we're talking about is I think in July 12th and 13th, we're proposing a workshop at APL to address the requirements for such a lunar proving ground, that what are the attributes that need to be verified and validated. So what attributes would the terrestrial pilot plant need to be tested? What attributes need to be tested and things of that nature? So we're actually behind the curve. You guys are like ahead of the curve on this one. Hopefully we can help you out.
Very good. So Ian, you're next. I think if I'm well informed, you are a scientist also by education. So why did you decide to change into a management role then?
I think originally was I wanted to be a footballer, but I wasn't good enough, so that's why. No, I think it's one of those things. As a scientist, you learn a lot, and then you want to hopefully inspire or train the next generation of scientists, so you can do that in a management role. I think as well, and I don't know if people in the audience can relate to this, you excel as a scientist, and then you're sprung into a management position. You've been a scientist for 10 years, you've been trained to do that, you become a manager with no formal training, and it is a baptism of fire, and it's something I think that a lot of us learn and a lot of us go through I've definitely gone through that, and hopefully now, with that experience, I can pass that on to the scientists within, Metalysis and wider today to help them excel and progress as they see fit.
So you're working since many years for Metalysis. You have a huge experience in operating test facilities, maybe not primarily for oxygen production or for metal production, but can you share some of the key lessons learned in operating these facilities in terms of scaling up, in terms of versatility? Is there something we need to take on board when we plan for the pilot phase of the pilot plan, sorry?
No, of course, no, happy to share that. I would say in some respect, they seem very common sense things to say, but hindsight's a wonderful thing of working on the process for a long time. So I would say when scaling up at the outset, ensure that your concept is scalable. And so sometimes you can think this works today at the small scale and it serves a purpose, but you always need to have the long term in view. I think that's the same as well for your materials that you choose of construction of the plant, etc., to ensure that they, again, are scalable. I would say as well then that the utilities that you use, again, that in using them, when you use them at scale, you're not using them in excess. And I think there's, as spoken about this morning, there's a great synergy between things that are happening in sustainability on Earth and critical materials, criticality of materials, the circular economy of really now, at the outset, the design, when you're designing your plant, you have to design it for the end of life as well, and for repurposing or reuse. And so I think that's an important thing to take into account. And I think one of the real big things as well is knowing what your skill base is and what it isn't and where you need help. And as well, I think one of the big things is don't reinvent the wheel. And so if there's something out there that somebody else has developed that you can use, it saves you time and money to use that to get your plant or whatever running in the shortest time possible.
Thank you. So Pascal, you're working for AirLiquide, and I think you also had a career change from an R&D manager to business developer. Again, why this change, and when?
Yes, previously, yes, you won't believe it, but I was an engineer, and now I jump into the dark side of the work, being a business development manager for space exploration. But I think that was a personal choice because the space exploration, and especially the moon ambition, is really growing. There is a growing interest in this, growing activity, targeting the moon. And what was really, really motivating to contribute as part of AirLiquide to meeting this ambition, to contributing to developing an economy on the moon and developing technologies to be able to unlock sustainability on the moon and the sustainable presence of human on the moon.
Thank you. So we heard a little bit about this open architecture concept, and in fact, it makes the development of the ground-based pilot plan more costly and more complex. So from your perspective, do you have any experience in open architectures for testing, and what are the pros and cons? And how far can we go with an open architecture?
So in AirLiquide, we do not have many open architecture, mainly for one reason, that could be part of the cons of that kind of architecture, is that we have a lot of intellectual property that we need to manage, and we need to protect some of the information. So open architecture is really a good, I would say, a good thing, but for an industrial point of view, it has also to be considered as difficult to be managed, since we have to protect our IP and not to disseminate critical competencies and critical knowledge. However, what is really interesting in open architecture is that we can foster all the ecosystem, we can welcome all the talents to contribute to developing new technology. So when I'm talking about the fact that AirLiquide is not willing to do open architecture, this is mainly related to terrestrial market, on which we have strong competition. And this is also the core business of AirLiquide. But if we look now at the moon, if we look at the ambition of setting human on the moon and developing ISRU, this is now different, because we need to have a collaborative approach. And so for that, I think, and I do think, as in the name of AirLiquide, that this is mandatory to have an open architecture, to motivate all the people, all the university and the companies to contribute, to test their technologies, and to share their knowledge and experience in that endeavor.
Clear. So, Daniel, you're an architect and you work for Blue Origin. So, why is an architect today interested into space?
Yeah, I think I want to emphasize that I'm here as an architect, first and foremost, but I am a space architect as well, but my background is in building design. And when I think about space resources, I can imagine all the different possibilities for using materials in space, for construction, for development, for different applications like life support. But it's important for us to learn how to work with resources in an intelligent way, not just for going to space, but for being able to apply that technology back in terrestrial applications. And as a space architect, I work on habitation, I work on different kinds of architectures, mobility. But what's interesting is that, you know, I find a lot of similarities. It's like systems engineering, it's conceptual design and creativity, and all tied together by working collaboratively, as you said. And what makes me, I think, excited about what you guys are planning to do is that you're going to build a facility where people can test ideas for using materials in a more intelligent way. And this could have repercussions that could lead to large-scale demonstrations and potentially in space as well. Yeah.
So I will ask you a bit more a soft skill question, less technical. Looking at the presentation, there's these huge challenges we have to address in advancing the topic of space resources. It means we need to attract the brightest talents, but we also need to keep them engaged for a very long time period. So how do we do that? I mean, we see there's huge interest, but will we have the same number of young engineers in 1, and 2, and 3, and 4 years? So how do we keep them engaged and attracted to this topic?
Oh, that's a good one. One way that I found, and this has been through a project that I worked on with ESA and MIT when I was at my previous company, was you have to really engage a lot of young experts, not just young, but also senior experts, to come up with long-term visionary ideas. You know, it's a collective way of imagining the future. And when you can have an imagined future, then people have a target, a goal to go after, like the Apollo mission. You know, this is something that mobilized a huge amount of resources and a lot of different minds. And so when you have that goal, you can engage generations. You can cross divides. International collaboration is a big one. And I think it really helps bring out the best in people. So if you can find a way to inspire that thinking, then you have no lack of manpower, I would say. You know, young minds willing to be a part of something like going to the moon. Yeah.
But, and yeah, a bit related, I mean, again, we have to work internationally. I've always said we need to work together, so different cultures. But we also need to work with lots of different market sectors, which is for space already a bit unique, because we work normally in the space community. Now we need to work with a mining community, with a robotic community. So how do you create an environment where you foster cross-collaboration between all these different cultures and different market sectors, where you think more commercial or more scientifically? And particularly at ESRIC, if you want to create this environment, what would you recommend to Kathryn to do in the next 5 to 10 years?
Yeah, so I mean, one thing that inspires me when I see technologies being developed out there is it's out there on display. You know, like you see launchers and robotics and experiments being done in a way where the public can participate. That inspires people. It inspires people to act. It inspires organizations to invest. And I think that's one of the components of any facility is there has to be a civic element where you put these things on exhibit. And if you can do that successfully, you not just educate the people outside of that, you know, that activity, but you also make the people inside proud to share what they're doing and to continue developing that and maybe even generate critique from others who might be experts and you just don't know it. Yeah.
Okay. So we still have some time. Pascal, I'm getting back to you. What is a good pilot plant? How big does it need to be? I mean, how representative has a pilot plant to be to actually be useful? Do you have any experience from the field you're working in on how do you define good requirements for pilot plant?
So personally, I cannot say that I have an experience. I've never built any pilot plant. But anyway, what we know in AirLiquide for doing a good pilot plant, first of all, let's just remind the objective. The objective of the pilot plant is really to find the limit of the technology to be able then to scale up to the final system. So if we want to do that, we need first of all to have versatility. This pilot plant must have plenty of sensors, measurement capabilities, must be versatile enough to integrate different technologies, test different products and systems. So this is the key. The first element really is the design to be capable of having this versatility of the pilot plant. Then I would say the second element is related to people. Operating a pilot plant, this is not easy. This requires different competencies from automation, from fluidic knowledge, from electricity, and so on. So plenty of different competencies have to be present in a few people that are capable of knowing perfectly the whole system and having the capability to debug and to understand what is happening inside this pilot plant. So I would say, first of all, the design aspect. Second, human aspect. Have the right people to operate and to understand what is happening.
Okay. Carl, you talked a lot about ground-based research and space-based research. And I think we all agree that sooner or later we need to have a pilot plant on the moon. But the path to getting there is maybe not yet so clear. So there is the need of ground-based research. Many can do it. Costs are lower. Space-based in situ demonstration are costly. Many fewer can do it. So if you would have 100 coins, you would need to invest in space-based and ground-based. How would you distribute it? And what is the right balance here to achieve if you want to accelerate the development of a pilot plant?
Yeah, good question. Excuse me, with a lot of layers to it. So keep in mind, ultimately, what we want to fly to the moon is a production facility that's capable of tens, even 100 metric tons of O2, let's say, whether from regolith or water ice per year. The question is, what role does a pilot plant have in terms of getting there? And I'd argue to finish off from the last response, I would add scalability. So a pilot plant definitely has to demonstrate scalability in terms of production. And other than that, it needs to demonstrate the entire process, you know, from delivery of the regolith to power to, you know, what I said before, basically the whole system of systems. And in that way, that is why I think this whole idea of a terrestrial pilot plant facility is such a good idea. We need to demonstrate this on the Earth if we're going to have a chance to demonstrate it successfully on the surface of the moon. And such a pilot plant, I would argue, does not necessarily have to only be a physical manifestation of what we're going to put on the moon. We have the capability of doing digital twinning. I'd strongly recommend that anything we do on the Earth would have a digital twin, so you can modify, muck with it, and then correct it again, and even make it an immersive experience for operators and turn it to a training capability for astronauts who will eventually use it. So I'm not sure if that addressed your question, but
no, you didn't answer the question on the 100 coins.
So I'm not sure what you actually
The 100 coins, how much would you invest in technology demonstration in situ? How much would you invest in ground-based research if you would be the business manager?
Oh, I'd invest at all both places equally. No, okay. The moon, to get something to the moon is very, very expensive, right? And you cannot simulate everything on the Earth that you need to demonstrate on the moon. So I would definitely, we have to do this on the Earth, but you've got to demonstrate it on the moon. There's just no choice there. And that's the expensive part. That'll be most of the coinage.
Okay. Thank you all for your engagement. I think time is up. Please answer our questionnaire, which was introduced earlier. And I think I give back to you, Lisa.
I I have a question for you, Bernhard. You, I don't have any questions that I can see online, but of course you can send them in. Why do you do what you do?
Oh, right. I wanted to do it since I was 8 years old. So I just I work on my youthhood dream, so to say.
That's a very concise and perfect answer. Thank you so much, Bernhard. And just to close the session, please welcome back to the stage Melchiorre.
Okay.
Thank you, the panelists. Thank you, Bernhard. And we hope that most of you will help us to go forward with the engagement that we plan to do probably in Q3 or Q4 in relation to the pilot plant. Because as we heard from everyone, really this is a community effort and we need to be aware of the needs and requirements that the community has. Because that's the only way that we can ensure that we can design something that is valuable for the community, and not just the European community, but everyone that wants to come and play. Thank you.